Let's talk about rocks, baby. Let's talk about the world we see. Let's talk about all the good times and the bad times the earth has seen. Let's talk about rocks. Hello, everyone, and welcome to the Dorky Dunkleosteus. I'm so happy to have you here again. I am your curator, Carla, and like I said, today we are going to be talking about rocks. I think I'm going to start a little mini-series called Geology 101, where we talk about some of the introductory information for anybody interested in getting into the field of geology. So the first thing we're actually going to do and talk about today is the RAC Cycle. What's your type of rock? So there's three major types of rocks. There's sedimentary, igneous, and metamorphic. These are basically the only types you'll really see, with the exception of extraterrestrial rocks, but even they could be considered igneous rocks from outer space. They're in a classification all their own. That's a fun topic we can get into in a different episode. So let's talk about these three major types. First up, let's talk about sedimentary rocks. These are made up of tiny, tiny rocks. Sedimentary rocks can be made up of anything from big rocks like this size, all glued together into a single boulder. Oftentimes what you'll see is actually more sandstones, which is actually sand that has been cemented over time to form a rock. Sedimentary rocks are generally very fragile, generally because they're not actually cemented together very strong. There are some exceptions to that. The limestones. Limestones are what we know as chemically cemented rocks. So limestones happen in sedimentary rocks over time in which water has gotten through and actually degraded or dissolved certain chemical elements inside rocks. Usually this happens in oceanic rocks or oceanic sediments, because a lot of seashells actually use calcium carbonate, which becomes limestone. Calcium carbonate, when it's hydrated and when it's degraded over time, actually cements together and makes a very, very strong sedimentary rock. Some examples of this are limestone, dolostone. All of those kinds are chemically cemented, and they are tough. I live near Niagara Falls, and the capstone to Niagara Falls is dolostone. It is completely sedimentary, but it will crack an 8-pound sledgehammer. These rocks are very hard to get through, but they also tend to be very fossiliferous. Most of the time, their fossils are microscopic, though. If you want bigger rocks that have, well, bigger fossils, you're going to look for something like sandstone, mudstone, these kind of rocks that generally have a fine but not super, super fine matrix. And from there, you will get some generally very well preserved fossils. Fossils are still incredibly rare, but they are most often found in sedimentary rocks. When it comes to physically cemented rocks, that's basically what happens when you have pressure over time, just kind of pressing and pressing and pressing, pressing and pressing layers of sediment together. This is where you get your limestones and your sandstones. They're generally not chemically fused, so even though they are solid and they take a bit of time to wear out, they do wear out very quickly over time, and they will break with a good hit on a rock, with a rock hammer. So that's pretty much the two major types of sedimentary rocks. You have your chemically cemented and your physically cemented. You will find fossils in both. And depending on where you are, you can get some, like the breccia we have as an example right over there. You can have actually a sedimentary stone that's filled with larger stone pieces. These are really cool because you can actually tell a lot about what that piece of sedimentary rock has gone through by looking at the rocks that make it up the rock. They're fascinating. I love them. Sedimentary rocks are the most common, mainly because most of the world has sediment, and these sedimentary rocks break down very easy and they make sand. This is where we get our sandstone. In fact, sand itself is made up of different types of minerals and sometimes many little tiny microscopic pieces of rock, which can be mostly, they are igneous. So we'll get that in when we get to the igneous, which is next. Igneous rocks. Igneous rocks are cooled magma or cooled lava. There is a difference between lava and magma. Magma is what is already underneath the ground. Once magma comes to the surface, it is lava. It is incredibly hot. It is melted. But it makes some really interesting things. There are different types of lava that you can get, but we're just talking about igneous rocks right now. So they're generally volcanic in nature. They can be non-volcanic in that you could have a magma chamber or just a bubble subsurface to the earth crust, and it can cool over time. This cooling will create something we know very commonly as a granite. Granites actually have a perfect threefold, I was going to say threefold law, but that's something else. Three-part recipe. They're 33% feldspar, 33% quartz, and 33% biotite. If you have a rock that is 1/3 of those three, you have a piece of granite. Now, there are some granites in the field of stoneworkers that aren't actually granite. So if you see a very pink rock, actually I have an example of this because I collect rocks. So, my basket of rocks here. Nope, that's a sandstone. That's a sandstone. That's a mudstone. Okay, here we go. So this is a piece of granite that's actually very pink. In the field, we would just call this a high feldspar, K feldspar specifically, K being potassium feldspar granite. So that means it has a greater percentage of potassium feldspar than any other kind. So it's greater than 1/3. It's still considered a granite, but you can, and this is when it comes to places that do memorial stones, this would be considered a Canadian pink. So it's a very tough rock. I've had this for years. You can see it's very, very sparkly. That comes from the biotite in it, as well as some of the quartz crystals. It's very dusty too. But you can have a lot of other things. You can have a pure black, which is mostly basalt. It's not a granite. Basalt is a very tough type of rock that actually makes up a majority of our surface, or rather our base for basically the continents and the bottom of the oceans underneath all that sediment. So basalt is incredibly tough. It's also incredibly dense. Basalt tends to be very iron heavy, so it is very, very, very heavy. So, there are volcanic rocks, of course. So one of the cool things I'd like to talk about is the lavas. So you can get two types of cooled lava that will form some really cool things. So the first type is A'a. These are both going to be Hawaiian names. Because we really recognize these from Hawaii, and that's where we really got to see the differences. So A'a lava is very sharp and spiky, and the way I remember it is if you were to walk across it barefoot, you go, ah, 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 ah. I'm weird like that, and that's how I remember things. So A'a generally is very vascular, meaning that it has a lot of air pockets. So those air pockets will either burst or break as the lava is cooling, and create jagged edges. And of course, then as it breaks, it creates jagged edges. The other type of lava that was once cooled, it creates is pahoehoe. Pahoehoe is very soft. It's also known as pillow lava. It's very soft, very smooth. It's very pretty, and it looks like you could just lay your head on it and go to sleep. So that's the two major types of volcanic rocks that we can get. So the other cool thing is that sometimes we can actually get fossils in igneous rocks. It's incredibly rare, but it does happen. Now, you're not going to find a dinosaur bone in igneous rocks. No, what you are going to find are trees. They're super common in Hawaii because Hawaii and the islands of Hawaii are incredibly active volcanically. So what happens is lava will pass by, or usually over, vegetation, and it's lava, it's hot. It will burn the vegetation. That vegetation, though, has a very high water content. that water content will actually be released as steam, and it will cool the lava around it. So as the lava forms around, say, a tree, like in our example right here, it will actually harden, and as the tree burns, and the tree will eventually burn to a point that it will degrade and it will rot away, you will get a trace fossil or a cast of the external portion of the tree. This is super cool, and it does happen. So no, igneous fossils do exist. They're incredibly rare. They're generally found in Hawaii or other areas in which there's a high amount of vegetation with a high water content and a very active volcano nearby that's very active and flowing. That's not to say something like Pompeii isn't an igneous fossil, because they are. So they are preserved in the way of a pyroclastic flow. So those would be considered fossils. Very cool. Also, it's amazing how well they are preserved. Pyroclastic flows are another form, but they generally incinerate everything. When it does happen, though, and we do find evidence of pyroclastic flows like Pompeii in the world, and we have human bodies, effectively, human people that are dead but look as though they are simply sleeping, it's really cool. There's been some amazing discoveries on the island of Pompeii over the years, discovering horses that were covered by people trying to save the horses and protect them. Of course, children as well, being curled up with their mothers wrapped around them. Very tragic, but amazing because it's a snapshot of life in Pompeii. And of course, we still have their houses, which are very well preserved, and we can actually get some paints. So igneous fossils exist. Don't let anybody tell you otherwise. They're just very rare. Next, we have metamorphic rocks. Metamorphic rocks are rocks that were once either igneous or sedimentary, or sometimes even metamorphic rocks that went over a change. So just like how we talked about in sedimentary rocks, that they would, have that heat or that pressure over a long period of time to cement them together. Well, if you add that long period of time under a lot of pressure, but also a lot of heat or a high temperature, you can get actual change in the rock itself. So the picture that we have here is slate. Slate is actually, it was originally a sedimentary rock called limestone. Limestone, when it's under a metamorphic process, will become slate. So this is kind of cool because there is a specific type of slate called Galveston slate, which it went all the way just to the brink of the melting point for that rock, and then came back to cool temperature. Galveston slate is very common in Galveston, Texas. And the reason why it's so cool is it's an incredibly tough roofing slate. So they use that a lot in roofing, as roofing tiles in Galveston. Unfortunately, due to the Galveston hurricane in the early 1900s, those slate pieces and tiles were so tough that they actually cut through trees and buildings during the hurricane. So slate is pretty tough. It's really kind of an amazing rock rather, that can have fossils in it. It's a little trickier, though, when it comes to metamorphic rocks because they are going under actual physical change, both chemically and physically. So what will happen is that the rock itself is not happy at the surface temperature. It's very cold. They are frozen. So generally, if it's very quickly cooled, something like, say, a type of igneous rock that's maybe cooled a little quicker than it really want to, it will want to be chemically stable. Most rocks are not. Metamorphic rocks actually become more stable because they've been put under so much pressure and heat over time that the chemical balances inside of them, the chemical structures, actually have time to break apart and restructure so that they will become more stable. That's what happens with slate and all that. What also happens sometimes during this is sometimes there will be fossils inside of them. Metamorphic rock fossils are really interesting. So we have a picture here of a trilobite fossil that is from the Ordovician period, and it's actually in a metamorphic rock. So that originally was probably a mudstone or a type of sandstone, a very fine sandstone. Judging by it, I would say it was probably something like a limestone or maybe a sandstone. and it underwent so much heat and pressure with a trilobite actually fossilized within it that it began to deform the fossil itself. It didn't destroy the fossil, but it deformed it. The cool thing is trilobites have a distinct ratio of their body parts depending upon species. So we can actually, if we do a whole bunch of complicated math and we know some constants, we can actually figure out exactly, stop that. We can figure out exactly how much pressure, how much force that rock underwent to form this new rock. You can do that also with crinoid stems because they are nearly perfect circles. And if you find one that's oblong or twisted or something like that, that's not just a damage from being fossilized, you can figure that out. We also can do this with brachiopods because brachiopods have a perfect 90-degree angle from their hinge point to along their opening. So it's a perfect 90-degree angle. So if we find one that's like that, and we can see that it's undeformed over time and the rock itself is also metamorphic, we can figure out the actual force that it was underwent. I actually did a paper on this during my undergrad. So let's talk about the rock cycle. All rock will be or was another type of rock. All rock is equal. Yeah! So every single rock was another type of rock at some point. All rock also will become magma again. That is because of how our system, or rather, how our continents, I've got rock dust all over me, how our continents actually move, and the fact that we have tectonic cycles and we have an actual liquid, semi-liquid, not too sure, core at the center of our planet. So when you have two plates meeting, you'll have generally one that will go under another, and this underground, this one plate that's going under will eventually melt and turn back into magma. That magma will then generally come up onto a volcano or get attached to a volcano, come up and become igneous rocks. That can either become metamorphic rock by putting under heat and pressure, or it can break down over time, such as our weather, our atmosphere, or even physically us breaking it up to make things. It will go through and become a sedimentary rock, or rather it will become sediments that then have a chance of becoming a sedimentary rock. Now, sedimentary rocks can be put under heat and pressure and become a metamorphic rock, or they can break down by weathering and erosion back into sediments and become another type of sedimentary rock. And then you have, just continue on and becoming metamorphic rocks. Metamorphic rocks can break down into sediments, or can remetamorphosize into a different type of metamorphic rock, or a finely metamorphic rock. That's always interesting. Or just continue to melt back down into magma. Now, there are a couple of things that are really kind of cool. So we see on the surface, like I said earlier, a lot of our grave markers are granite. They used to be marble, which is a metamorphic rock, but it's not very stable. Metamorphic rock actually dissolves very quickly at the surface, especially when it comes to acidic rain, which we now have much more of. So when you see something, around here we actually do have grave markers that are made of marble, usually from the Civil War or around that time period. The War of 1812 is pretty common as well. They're actually very hard to read. So, and that's been a couple hundred years. That's a lot of degradation. Now, if we use granite, we actually don't see that degradation very quickly over time because the granite tends to be more stable at the surface. We wouldn't use a sedimentary rock because we can't trust that it'll stay there, and also most sedimentary rocks are very difficult to sandblast because they'll just break apart. Because most rocks are either physically or chemically weathered or chemically sealed, or rather chemically composed, or physically or chemically, and that will break down a lot quicker over time as to say something like a metamorphic or an igneous rock, which literally has crystals that have grown into a latticework that's very, very strong. So there are some things that are not considered rocks that often we see, especially with volcanic rocks. I actually have a new sample here. So this is a, Ow, very sharp. This is a obsidian arrowhead, and this is a modern arrowhead. So it's obsidian glass. I'm being very careful not to cut myself. That was probably really stupid to do that because it is very, very sharp. So this is actually natural glass. Glass is not a mineral. It does not have a finite crystal structure. So it's technically not a rock. It's just glass. But it is igneous in origin. Now, the cool thing about obsidian is because it's not stable, it is super not stable. It has no structure at all. It wants to be stable. So if I were to put a camera on this for all of time and have it just recording all the time, in a few thousand years, we would actually see it turn into snowflake obsidian. Snowflake obsidian is when the obsidian inside of it, so the glass, which is actually SiO2 or silica, when the silica inside of the obsidian actually becomes stable because it starts to recrystallize. That's weird, right? Well, think of it this way. When you have an ice cube, at the surface, it's not happy when it's not outside of the freezer, and it'll melt. Well, ice will also do something called sublimate, or become a gas. Ice is technically a mineral because it has a fine crystal structure, and it will reform. So we can actually see it's almost like a sublimation in obsidian, where over a long period of time, the SiO2, which is quartz in the glass, will start to move around actually nanoscopically and begin to form quartz crystals. Those quartz crystals then form more quartz crystals, and they begin to flower out, and it makes snowflake obsidian. So it's really beautiful because it literally looks like snowflakes that are growing. But eventually the entire thing will recrystallize into an unstable, but more stable than obsidian actual mineral because it will be quartz. So eventually this will become a quartz arrowhead instead of an obsidian arrowhead. But that is far beyond my lifespan. In fact, it's far beyond anyone who is probably alive now or alive in the future. It takes several thousand, if not a couple million years. Well, I would say a couple thousand, 2,000-3,000, and obviously if we were to make it to a million years, millennium's confusing. Tens of thousands is more like it. It would eventually become a quartz crystal. So all rock is recycled. Like I said, even something that isn't a rock will eventually become recycled. This will break down over time. Just like, you see sand, this will eventually become something like black sand. That's what black sand is generally obsidian or basalt, stuff that's been weathered out over time, over a very long time. And that will eventually become a sedimentary rock. So thank you for joining me on an introduction to geology, or Geology 101. Short video, but I think it's kind of a lot of fun to do these more shorter videos talking about some introductory discussions. Here are my sources. A lot of it's from geology.com. I highly recommend the site. It's a really cool introduction. We also have SF College for the RAC Cycle, and some great photos from the trees, the lava trees, and the deformed trilobite. If you are interested in continuing on to get your geology degree, that's awesome. I'll be here to help. If you have any questions about geology or paleontology or anything, leave them down in the comments below. Right, I can use my arrowhead. Leave them down in the comments below. I would love to hear them. If you like the video, leave a like. Give me that thumbs up. I'd love to hear it. And also, make sure you subscribe so you can notified when we go and upload more videos. We upload every Monday at 9 a.m. And also ring the bell, because if you're ringing that bell, you will know when we go live. This weekend we will be going live again with another episode, or rather live stream, because I'm sure I'm going to scream at some point, of Ark Survival Evolved. New Island, I haven't done anything with it yet, so I'm going to be completely a purist, and I'm going to make sure that that world specifically is all for the stream. So we will go through, unless you guys want to see me actually do some basically some building and kind of level building and getting rid of all that boring stuff like me going to find food, which I need to do at some point in that game. You know, hey, that's what we'll be doing this weekend. Hopefully we'll do it at Friday. Yeah, we'll be doing it on Friday night, so keep your calendars open. Make sure you have that ring-a-ling ding 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 bell, because that will let you know when I go live. All right, thank you again so much for joining me. I am Carla, your curator. Everyone have a great week, and remember, keep digging. Bye-bye.